Hey guys, this is the last video of my MAT 271 final project. The last question is going to be dealing with average and instantaneous rate of change. And like in the last ones, we're going to read the problem and then we're going to go ahead into the workspace and solve this problem. Okay, so the last question states, find the average and instantaneous rate of change when y equals the square root of x plus x to the fourth plus 5x cubed plus 12x squared plus 3 over 2x plus 20 when x is equal to 6. Okay, so that's a lot of variables, obviously. But average and instantaneous rate of change are really not that hard to understand. Yeah, average rate of change, that's finding the slope of the secant line of the graph, and the instantaneous rate of change is finding the slope of the tangent line. Okay, so we're going to go into here real quick. I'm going to solve this problem right here, all right? So this will involve quite a bit of repetition and writing, which is fine. Let's get practice in. So first what we're going to do is I'm going to go ahead and rewrite part of the problem. So instead of using the square root, which is kind of ugly and we don't want that in there, we want to use some pretty easy variables. We're going to change that to x to the 1/2 power, and we're just going to rewrite everything else. X's look like y's, sorry. X cubed plus 12x squared plus 3 over 2x and plus 20. Okay. From there, we're going to take the derivative because we're trying to find the slope of the, well, first we're finding the average rate of change. We're going to be taking the slope of this graph right here. So that's the derivative. And then we're going to plug in what x equals to 6 to find that average rate of change. And basically what that means is the average rate of change basically means what's the average slope across the entire graph for the majority. Okay, so y prime, which is the derivative, and there's going to be a lots of power rule right here. So first we're going to do first one, which is going to be you bring the power to the front, multiply it to the front, and then you're going to subtract 1 from the initial power. Okay, so that means this is going to be 1/2 x if we bring 1/2 to the front. Then we subtract 1 from 1/2, and we get negative 1/2. Okay, same thing for here. X to the fourth, you get 4x cubed. And here again, 15x squared plus 24x plus 3 over 2. And then constants derivative are always 0. So we don't even have to put that in there. Okay. So now we have our derivative. This is the equation for the slope of the secant line. Okay. And now what we're going to do, we're going to take our x value, 6, and we're going to plug it in to our new equation. And so doing that, plug in 6 for x, and we're going to get y prime is about, say about because it's we round it upward. We plug into the calculator. It gives us about 15 or 1,549.70. All right. And this, once again, this is the average rate of change for the slope of the secant line of that graph. Okay. And then with that knowledge, we're going to try and find the instantaneous rate of change for this equation as well. Now, the instantaneous rate of change is the slope of the tangent line. This is for an initial moment on the graph, which will be, and depending on what numbers we use on the limits, will determine how close we get to this average rate of change number. Okay, so the closer to the x value we are, the more accurate the number is going to be to give us that slope of the tangent line. Okay, so I'm going to go ahead and clear this off. Okay, and so from there, well, I'm going to rewrite the average so that way we have an idea of what it was again. So average equals 1549.7. Okay, so for instantaneous, our equation is going to be f of b minus f of a over b minus a. You may have also seen it as like y2 minus y1 over x2 minus x1. Okay. These are both the same exact equations. I'm just going to go ahead and use the first one that I wrote down because I feel like that's the easiest interpretation of it. Okay. All right. And so f of b minus f of a. B and a are going to be the limits or the numbers that we're going to be using to determine that instantaneous rate of change. Okay. And so, like I said, the closer to 6 we are, the more exact the number will be. Okay. So I think two good numbers would probably be maybe for A we can do 5.9, and then B we can do 6.1. Okay. And then our A coordinate is our X coordinate, and our Y coordinate is our B coordinate. Okay. Erase this so it doesn't confuse anyone. Okay. So now from there we're going to plug this into our equation that we wrote out. So we have f of 5.9. Oh, sorry. Wrong order. So f of 6.1 because b is first. Okay. Minus f of 5.9. Okay. All over 6.1 minus 5.9. Okay. And like we did with the x value for our finding the average rate of change, we're going to plug in these values not into the derivative of the equation, but into the original equation because we're only doing f of b and f of a, which is y. Okay, so or y as in like y, the equation is set equal to y. So f of b is equal to y of 6.1. Okay, so plugging these into the calculator. I've already got the answer for the first one, and for f of 6.1, that gives us around 2,997.62. And then for f of 5.9, plugging that back into the original equation once again, that gives us around 2,687, just about. Okay. And then we're doing this all over 6.1 minus 5.9, which gives us 0.2. And then we simplify this. And this gives us an answer of around, plug it into the calculator real quick, 2,997.62 minus 2,687. That gives us 310.62 divided by 0.2. And that gives us 1553.1. And as you can see, these numbers are somewhat close. They're off by about 4 units, but like I said again, they're not always going to be the exact same, but they're going to be fairly close because the instantaneous rate of change is just at one moment, while the average is accounting for all the slopes across the curve. Okay? And so this is our instantaneous rate of change right here. All right. And this is our average. Okay? And that will conclude my presentation.